Hello friends, welcome to a lecture series on matrix analysis with applications. Now today's lecture is based on eigenvalues and eigenvectors, that if we have a given matrix A, then how can we find its eigenvalues and the corresponding eigenvectors. So first of all, what eigenvalues and eigenvectors are? So let V be a vector space over the field F and T be a linear operator on V. Okay, that is T is a linear transformation from V to V. A non-zero vector V belongs to V is called an eigenvector of T if there exists a scalar lambda belongs to F such that TV equal to lambda V. So if we have a linear operator T and we have a non-zero vector V in V and there exists a lambda belongs to field such that TV equals to lambda V, then we say that lambda is the eigenvalue and the corresponding eigenvector is V. Now a square matrix A may be viewed as a linear operator T and is defined as Tx equals to Ax where x belongs to V. Okay. So if we have a linear operator, then then a matrix can be viewed as a linear operator also. Now let us define a matrix A which is a square matrix of order n. Then if we consider a system of homogeneous equations Ax equals to lambda x, then the value of lambda for which the system of linear equations has non-trivial solutions are called eigenvalues or the characteristic values of A, and the corresponding non-zero vectors x are called eigenvectors or the characteristic vectors of A. Since every matrix can be viewed as a linear operator T, so in the previous definition we have replaced this T by a matrix A here, and this x is in V. This is a scalar lambda in field. Okay. So what I want to say basically is, suppose you have a matrix A which is of order n cross n. Okay. Then if Ax is equals to lambda x where x is not equal to 0, then this lambda is called eigenvalue of A, and x is called corresponding eigenvector of A, or eigenvector corresponding to lambda. Okay. Now we are having Ax equal to lambda x. So this can be written as Ax minus lambda x equal to 0. Okay. Now this can be written as A minus lambda into I times x equal to 0, where I is an identity matrix. Now what we are having basically, we are having A minus lambda I x equal to 0 means we are having system of homogeneous linear equations, because right hand side is 0. Okay. Now since x is not equal to 0, as we already defined in the definition, x is not equal to 0. So this means if we are taking this as a linear operator T, if we take A minus lambda I as a linear operator T, then Tx equal to 0, that means and x is not equal to 0, that means the nullity, the null space, the nullity of this matrix or this operator is greater than equal to 1. Okay. Because x is not equal to 0 means because this means nullity is not 0, and nullity is not 0 means it is greater than equal to 1. Now what is the dimension of A minus lambda I? Of course dimension of A minus lambda I is n. So by rank nullity theorem, the rank of this A minus lambda I plus nullity of A minus lambda I must be equal to dimension of matrix or operator which is n. So, this implies rank of A minus lambda I must be equals to n minus nullity of A minus lambda I, and since nullity is greater than or equal to 1, this means this is less than or equal to n minus 1. And since rank is less than or equal to n minus 1, less than or equal to n minus 1, this means in the echelon form of this matrix at least one row is there which is having all 0 elements, and that means this implies determinant of A minus lambda I must be 0. Now, this equation determinant of A minus lambda I equal to 0 is called a characteristic polynomial. This will give a characteristic polynomial in lambda, characteristic polynomial of lambda. Okay. Now this is a matrix of order n cross n. So, determinant, so this determinant will give a polynomial of degree n in lambda. Okay. So what we are having now? So, now if we visualize the determinant of A minus lambda I equal to 0, that means this determinant is equal to 0. Okay. You see, if we are taking determinant of A minus lambda I equal to 0, so it implies that determinant of A is this matrix, you see A11, A12, if you are taking this matrix as A, and AN1 up to ANN, okay, minus lambda times I is identity matrix. So, when you take determinant put it equal to 0, so this is nothing but determinant of, you see, only this lambda will be subtracted from the diagonal elements because all other entries are 0. So, this will be determinant of A11 minus lambda, A12 and so on up to A1n, then A21, A22 minus lambda, then A2n and so on AN1, AN2 and so on up to ANN minus lambda. This determinant is equal to 0. So, this will give us a polynomial in lambda, and that polynomial is called characteristic polynomial. Okay. So, this is basically gives minus 1 raised to power n, lambda raised to power n minus say C1 lambda raised to power n minus 1 plus C2 lambda raised to power n minus 2 minus and so on plus minus 1 raised to power n into Cn is equal to 0. Okay, because when you expand this in terms of lambda, so you will get a polynomial in of degree n in lambda. Now if you carefully observe this determinant, you see when you open from the first element, you see if you take A11 minus lambda, then you delete this row and this row and this column. So, this will be the remaining determinant minus A12. Now, when you expand from this element, you delete this column and this row, that means the two values of two linear factors of lambda are not coming in this expansion. So, that means this expansion will contain maximum lambda raised to power n minus 2, because when you expand from this, you are deleting this row and this column. So, two factors of lambda are not coming in the expansion. That means the maximum power of lambda which is coming from this term is lambda raised to power n minus 2. Similarly, if you take A13, so here will be something A33 minus lambda, and when you delete this column and this row, then again two factors of lambda are not coming. So, that means maximum power of lambda which are coming from this term is lambda raised to power n minus 2. Similarly, from the other terms. So, what we can conclude that the remaining terms will contain say alpha 1 lambda raised to power n minus 1 and so lambda raised to power n minus 2 and so on. So, that means the power of lambda raised to power n and power of lambda raised to power n minus 1 are coming only from the first determinant. Now if you see here, again if you see here, now if you open from this is okay. If you open from this, here is something A33 minus lambda is again here. If you open from this element, again you will delete this column and this row. So, 2 powers of lambda are not are still not here, I mean not coming. So, that means you see, if you take A11 minus lambda, if you expand this determinant, then it is A22 minus lambda and again some determinant plus and minus A23 and determinant of some other thing, which in which 2 powers of lambda are not there. Okay. So, that means it will contain maximum lambda raised to power n minus 2 and minus 3, because this this determinant is having lambda raised to power n minus 1, one factor is already outside. So, this determinant is having lambda raised to power n minus 1 and 2 factors are not coming, that means the maximum power which this element is having is lambda raised to power n minus 3, and when you multiply this with lambda, so it will be having lambda raised to power n minus 2. So, that means what I want to say basically that when you expand similarly the entire determinant, so lambda raised to power n and lambda raised to power n minus 1 are only coming in the product of the diagonal elements. When you similarly try to expand this entire determinant, so lambda raised to power n and lambda raised to power n minus 1 is coming only from the product of the determinant diagonal elements. Okay. So, and all other, and the lambda raised to power n minus 2, lambda raised to power n minus 3 are from all the components, maybe from all the components, all the elements. So, that means coefficient of lambda raised to power n is simply coefficient of lambda raised to power n in simply A11 minus lambda, A22 minus lambda and so on ANN minus lambda, and it is simply minus 1 raised to power n. You carefully see, it is simply minus 1 raised to power n. And similarly, if you want to see coefficient of lambda raised to power n minus 1, it is simply coefficient of lambda raised to power n minus 1 in again this product A11 minus lambda, A22 minus lambda and so on up to ANN minus lambda. So, what is the coefficient of lambda minus lambda raised to power n minus 1 in this? It is simply A11 plus A22 plus and so on ANN. You can simply see the sum of these elements A11 plus A22 and so on up to ANN will be the coefficient of lambda raised to power n minus 1. Okay. So, what basically now we are having determinant of A minus lambda I is something like minus 1 raised to power n, and it is lambda raised to power n minus C1 lambda raised to power n minus 2 and minus 1 plus C2 lambda raised to power n minus 2 minus and so on minus 1 raised to power n Cn. So, this is equal to this. Now, so how many roots this equation will be having? This equation will be having n roots, because it is of n degree polynomial. So, let lambda 1, lambda 2 and so on up to lambda n are the roots, be the roots of this equation. Okay. So, if these are the roots, then what is the sum of the roots? You can simply see the sum of the roots is simply, okay, this is the equation. So, sum of the roots of this will be simply negative of minus C1, okay. It is minus negative of minus C1, and this is equal to basically, this is equal to you see the coefficient of lambda raised to power n minus 1 is simply this. So, this is A11 plus A22 and so on up to ANN, and this is called a trace of a matrix, A. So, what we have concluded? We have concluded that sum of eigenvalues is nothing but the trace of the matrix, that means sum of the diagonal elements, the first property. The second property is, now this result, that this is equal to this, holds for every lambda, for any lambda. Okay. So, this hold for lambda equal to 0 also, and when you substitute lambda equal to 0, we will get determinant of A as equal to Cn, okay, as Cn. Now, if you find product of roots for this equation, product of roots. So, product of roots are lambda 1, lambda 2 up to lambda n, and that is simply equal to, you see it is minus 1 raised to power degree of equation, last term upon first term, which is nothing but Cn, okay, Cn upon minus 1 raised to power n, and that is simply equal to determinant of A. So, this implies product of eigenvalues is nothing but determinant of A. So, we have noted here two important properties of eigenvalues. The one property is that the sum of the eigenvalues is equal to trace of the matrix, that is the sum of the diagonal elements, and the second property is the product of the eigenvalues is equal to the determinant of the matrix A. Okay. So, the sum of the eigenvalues is simply equal to trace of the matrix, and the product of the eigenvalues is simply the determinant of A. Now, let us discuss this problem. The first problem is, let us consider this matrix A, which is 1 minus 1 1 1. Let us find its eigenvalues and the corresponding eigenvectors. So, the matrix A is simply 1 minus 1 1 1. So, you can simply write A minus lambda I, determinant, this must be 0 for the characteristic polynomial or for finding the roots of the equation, roots of the latent roots or the characteristic roots of this matrix A. So, this is nothing but 1 minus lambda minus 1 1 1 minus lambda, determinant equal to 0, and this implies 1 minus lambda whole square plus 1 should be 0, or 1 minus lambda square is equals to minus 1, that implies 1 minus lambda is equals to plus minus iota, or lambda equal to 1 plus minus iota. So, the two roots of two eigenvalues of this equations are 1 plus iota and 1 minus iota. So, these are the eigenvalues. So, let us find corresponding eigenvectors. So, first we find eigenvector corresponding to lambda equals to say 1 minus iota. Okay. So, how we will find that? You can simply see that A minus lambda I times x must be equal to 0. This we have already seen that this x is the eigenvector corresponding to this lambda. So, this implies, now we will substitute lambda as a 1 minus iota. So, this is A minus 1 minus iota times iota times identity matrix into x equal to 0. So, this implies, now when you take 1 minus lambda here, so it is you can simply take lambda here as 1 minus iota. So, it is iota 1 and it is 1 and it is again iota, it is minus 1, it is iota, and x is x1 x2 equal to 0 0. So, this implies, now you can apply some elementary row operation in this matrix. So, simply first interchange these two rows, it is 1 iota minus 1, x1 x2 will remain as it is, interchange these two also 0 0. Now, this implies you can make 0 here with the help of this by applying elementary row operation R2, this means R2 minus iota times R1. When you apply this elementary row operations here, it is 1 iota, it is 0, it is again 0, and it is x1 x2 0 0. So, this implies x1 plus iota x2 equal to 0. Okay. So, this give infinitely many solutions of x1 and x2. Okay. You can substitute any value of x1, you can find corresponding value of x2 such that x1 x2 should not equal to 0, of course. Okay. So, one such value is one such x1 is, you can simply take, you see x is what, x is x1 x2. you can take x1 as minus iota x2 from here, and it is x2. So, it is x2 times minus iota and 1, where x2 is any real number. So, if we are talking about number of linearly independent eigenvector corresponding to lambda equal to 1 minus iota, so it is 1. So, you can pick any one linearly independent eigenvector from this because it gives infinitely many eigenvectors. You can pick out any one eigenvector. So, we can say that vector is linearly independent eigenvector corresponding to lambda equals to 1 minus iota. So, we can say that corresponding to lambda equal to 1 minus iota, the linearly independent eigenvector is say minus iota 1 transpose. Now, similarly, you will take lambda is equal to 1 plus iota, and we can find out the corresponding linearly independent eigenvector on the same lines. Okay. Now, let us consider second problem. Here the matrix B is 0 0 2 0 2 0, and this matrix, it is given to us that the one of the eigenvalue of this matrix B is 4. Then we have to find the remaining two eigenvalues and also the corresponding eigenvectors of B. So, let us discuss this problem now. Here the matrix A is simply 0 0 2 0 2 0 and 2 0 3. Now, 1 lambda is 4, it is given to us, say lambda 1 is 4. Now, we know that the trace is equal to the sum of the eigenvalues. So, let us suppose the other two eigenvalues are lambda 2, lambda 3. It is of order 3 cross 3, so it will be having 3 eigenvalues. So, sum of the eigenvalues is equal to a trace of the matrix, that is 5, 0 plus 2 plus 3. Now, lambda 1 is 4. So, this implies lambda 2 plus lambda 3 is 1. Now, the product of the eigenvalues, we know that product of eigenvalues is simply determinant of A. Now, the determinant of A is simply when you simply open this matrix, I mean determinant, then you simply get it minus 8. Okay. Now, it is 4. So, this implies lambda 2 lambda 3 will be minus 2. So, solving these two equations, we can easily find lambda 2 and lambda 3. So, it is clearly as we are seeing, it is lambda 2 is 2 and lambda 3 is minus 1. So, sum is 1 and the product is minus 2. So, the other two eigenvalues are 2 and minus 1. Okay. So, now we can say that this matrix has the eigenvalues 4, 2 and minus 1. Now, we have to find out the corresponding eigenvectors. Let us suppose we have to find out the eigenvector corresponding to lambda equal to 4. Similarly, we can find eigenvector corresponding to lambda equal to 2 and lambda equal to minus 1. So, let us find eigenvector corresponding to lambda equal to 4. How you will find that? This is A minus lambda I x equal to 0 again. So, this implies A minus 4 I into x equal to 0. So, this implies minus 4 0 2, this is 0 minus 2 0, this is 2 0 minus 1, and x is x, which is equal to 0. This implies, now we will try to convert this into its echelon form. Okay. So, we will make 0 here with the help of this is already 0, we will make 0 here with the help of this. So, which operation we will apply? R3 to R3 plus half of R1. So, this is minus 4 0 2, this is 0 minus 2 0, this is 0 0, this plus half of this is again 0. Okay. Now, this implies minus 4 x1 plus 0 into x2 plus 2 into x3 equal to 0. If you are taking x as x1, x2, x3, you substitute it here and we multiply these two matrices, then we simply get these equations, and minus 2 x2 equal to 0. So, this implies x2 equal to 0, and x3 as 2x1. So, what is the corresponding eigenvector? Corresponding eigenvector will be you can see it is x1 0 and 2x1. So, it is x1 times 1 0 2. So, again there are infinitely many eigenvectors corresponding to lambda equal to 4, but if you are talking about number of linearly independent eigenvector corresponding to lambda equal to 4, so that is 1. You can pick any one eigenvector from this space. So, we can say that is the linearly independent eigenvector corresponding to lambda equal to 4. Similarly, we can find out eigenvector corresponding to lambda equal to 2 and lambda equal to minus 1. Okay. Now, if lambda is an eigenvalue of a matrix A and x is a corresponding eigenvector, then we have the following properties. Now, it is very easy to see these properties. You see here, see if A has a eigenvector eigenvalue lambda and corresponding eigenvector is x, that means Ax equal to lambda x. Now, if you want to calculate the eigenvalues of alpha A, where alpha is a non-zero scalar, then how we can find? You simply multiply these two by alpha, both sides by alpha. So, we can simply see that this alpha A has an eigenvalue alpha lambda and the corresponding eigenvector is A, corresponding eigenvector is x. Now, if you want for A square, you see Ax equal to lambda x, x not equal to 0. If you multiply both sides by A, it is A into Ax equals to A into lambda x, which is lambda times Ax, and Ax is lambda x, so it is lambda x. So, we can say that A square x equals to lambda square x. Okay. So, what we can say that if A has an eigenvalue lambda and the corresponding eigenvector is x, then A square has an eigenvalue lambda square and the corresponding eigenvector is x. Similarly, we can say that A raised to power k is equals to lambda raised to power k into x. You can simply similarly find A cube, A raised to power 4 and so on. So, what we have concluded? We have concluded that if A has an eigenvalue lambda and a corresponding eigenvector is x, then A raised to power k has an eigenvalue lambda raised to power k and the corresponding eigenvector is x. Now, next property is A and A transpose both have same eigenvalues. That is very easy to show. You can see that eigenvalues of are given by this expression. Okay. Now, A minus this matrix, the transpose of this matrix is equals to A minus the determinant of this is same as determinant of this, because by interchanging rows and columns will not change the value of the determinant. This is equal to 0, it is given to us, and this implies A transpose minus lambda I whole determinant is equal to 0. So, that lambda is not changing here, whatever lambda we are having here, same lambda we are having here, that means the eigenvalues of A and A transpose are same. The next is if you say that Ax equal to lambda x and suppose determinant of A is not equal to 0, that means A is invertible, then you can take A inverse both the sides, then A inverse of Ax will be equals to lambda times A inverse of x, and this implies identity into x equals to lambda into A inverse of x, and this implies A inverse of x will be 1 by lambda times x. This is one or identity. Yeah. So, we can say that if A has an eigenvalue lambda and the corresponding eigenvector is x, then A inverse has an eigenvalue 1 by lambda and the corresponding eigenvector is x. Okay. So, these are few of the properties of eigenvalues which is stated here. Okay. And if G lambda is an eigenvalue of Ga, where G lambda is a polynomial of lambda, where x is an eigenvector of Ga corresponding to eigenvalue G lambda. That is very easy to show again, because the third property itself states that if G lambda is a polynomial of lambda, then G lambda is an eigenvalue of GA. Now let us discuss these few problems quickly. You see, if A is a singular matrix of order 2 and having trace 3, if it is a singular matrix means determinant is equal to 0. Determinant is nothing but product of eigenvalues. Product of eigenvalues equal to 0 means at least one of the eigenvalues is 0. Now it is of order 2, that means it is having only 2 eigenvalues, say lambda 1 and lambda 2. Okay. So we can say A is of order 2 cross 2 having 2 eigenvalues lambda 1 and lambda 2, then product of eigenvalues is equal to 0 because matrix is singular and trace is 3, trace is 3. So here, from here we can say that one of the eigenvalue is 0, say lambda 1 is 0. If lambda 1 is 0, so lambda 2 will be 3. So the eigenvalues are 0 and 3 of A. Eigenvalue of A transpose will be again 0 and 3, and eigenvalue of A transpose square will be 0 and 9. Okay. The next one is, if A is a 4 cross 4 matrix of eigenvalues 1 minus 1 2 minus 2, then the eigenvalues of this how we can find? You see, eigenvalues of A are 1 minus 1 2 minus 2, and B is given as it is 2A, it is 2A plus A inverse minus I. So it is some polynomial in it is some polynomial in B, A. So the eigenvalue of B will be nothing but if A has an eigenvalue lambda, then the eigenvalue of B will be nothing but 2 lambda plus 1 by lambda minus 1. 2A has 2 lambda eigenvalue, A inverse has 1 by lambda eigenvalue, and this eigenvalue is 1. So simply you can substitute here. Corresponding to 1, we are having 2 plus 1 plus 1 minus 1 is 2 for B. Corresponding to minus 1, if you substitute minus 1, it is minus 1 minus 1, that is minus 4. Corresponding to 2, it is 1 plus 1 by 2 minus 1, that is 4 minus 1 by 2, that is 7 by 2. Corresponding to minus 2, if you are talking about minus 2, because minus 2 it is minus 4 minus 1 by 2 minus 1, that is minus 4 minus 3 by 2, that is minus 11 by 2. So these are the eigenvalues corresponding to B. So the third problem is simple. If A is a matrix of order n and such that A raised to power k is 0, where k belongs to a natural number, then all these eigenvalues are 0. Because if any of the eigenvalue is not equal to 0 of A, then A raised to power k will not be 0. Okay. So therefore all the eigenvalues of A must be 0. So this is a result that if A is a square matrix of order n having k distinct eigenvalues lambda 1 up to lambda k, let Vi be the eigenvector corresponding to the eigenvalue lambda I from 1 to k, then the set this is linearly independent. So let us try to prove this result. You see, lambda 1, lambda 2 up to lambda k are distinct eigenvalues. That means lambda I is not equal to lambda j for I not equal to j, number 1. Now the set we are considering this V1, V2 up to Vk. We have to show that this set is linearly independent. V1 is a eigenvector, linearly independent eigenvector corresponding to lambda 1. V2 is a linearly independent eigenvector corresponding to lambda 2 and so on. So we will prove this by the method of induction. Okay. Let us for n equal to 1, for k equal to 1, we are having V1, and V1 a single set is it is linearly independent. A singleton set is always linearly independent, singleton non-zero vector, and V1 is a non-zero vector, is always linearly independent. Now we will assume that it is true for k equal to r. This result hold for k equal to r, that means the set of k r vectors are linearly independent, and we will try to show that this also holds for k equal to r plus 1. So take the linear combination of these vectors now in order to show that these are linearly independent. Now, you multiply both sides by matrix A. So, we can simply take A into alpha 1 V 1 plus A into alpha 2 V 2 and so on, A into alpha r plus 1 V r plus 1 equal to 0. Now, A into V I is lambda I into V I for all I, because lambda I is the eigenvalue and the corresponding eigenvector is V I. So, we can simply write lambda 1, A V 1 is lambda 1 V 1, similarly alpha 2 lambda 2 V 2 and so on up to alpha r plus 1 lambda r plus 1 V r plus 1. Now, say this is equation 1 and this is equation 2. You can multiply 1 by lambda r plus 1 into 1 and subtract with 2. So, what we will obtain? We will obtain lambda alpha 1 into lambda r plus 1 minus lambda 1 V 1 and so on up to alpha r lambda r plus 1 minus lambda r times V r equal to 0. Now, we have already assumed that a set of r vectors is linearly independent. So, this is some linear combination of these linearly independent vector which is equal to 0. So, this implies alpha I is lambda r plus 1 minus lambda I equal to 0 for all I. But eigenvalues are distinct. So, this is not equal to 0. So, this implies alpha equal to 0 for all I. For all I means for I from 1 to r, and when you substitute alpha from 1 to r here with all 0, then you will get alpha r plus 1 V r plus 1 equal to 0, and since V r plus 1 is not equal to 0, it is an eigenvector. So, this implies alpha r plus 1 equal to 0. So, we have shown that all alpha i's from I from 1 to r plus 1 equal to 0, that means this set of vectors are linearly independent. So, in this lecture we have seen that what eigenvalues and eigenvectors are and some of the important properties of eigenvalues and eigenvectors. So, thank you.